Okay, folks, so in this video, I would like to go over some details from section 2.4 and 2.5 that I wish to have gone over with you in person, but we'll have to do it through a video today. So in section 2.4, we were introduced to, or reintroduced to, a lot of different structures. In particular, we looked at the absolute value function. And for the absolute value function, that was our V graph. And we said that for this V graph, we can think about the part of the graph on the left as negative x and the part of the graph on the right as positive x. So we were able to write this function as negative x on the left and positive x on the right as a piecewise defined function. So negative x when you have negative x values, positive x when you have positive or zero x values. I would like to go over this kind of problem to sketch another piecewise defined function. Now, this guy doesn't come from an absolute value, but these are good to go over because you come across them often in a lot of different applications. So our job is to sketch this function. Now, this function is defined one way on the left-hand side. When your x's are less than 2, your function is negative 2x plus 3. When your x's are greater than or equal to 2, your function is defined by 3x plus 1. Let's take a look at how to graph this function. So one thing you would like to note is that things change when x is 2. To the left of it, you have the yellow graph. To the right of it, you have the green graph. So on this left-hand side of the graph, you're going to have the graph of negative 2x plus 3. On this side of the graph, you're going to have the graph of 3x plus 1. Notice that for the left-hand side, the graph is simply a line. How many points do you need to generate a line? Just 2, right? So what you could do is plug in any two values of x that are less than 2 into this function. For example, you can plug in negative 1 or 0 and get two different y values. So then that will give you 2 points, and then you just simply need to connect the dots between those 2 points to graph the line of negative 2x plus 3. However, whenever you're doing piecewise applications, I highly recommend that one of those points that you're selecting be that 2, even though 2 is not a value that we're plugging into the function of negative 2x plus 3. So suppose that we plug in x equal to negative 1. When you plug in negative 1, you'll be working with the yellow part of the graph, plugging in negative 1 into that value of x. Sorry, it's gone a little haywire. You get 2 plus 3, that gives you 5. So we have negative 1 comma 5. So this is one of the points that we have on the left-hand side. And if we were to plug in 2 into the function negative 2x plus 3, we would have negative 4 plus 3, that's negative 1. So our point would be 2 comma negative 1. down here somewhere. Now, we're not going to include that point because the yellow graph does not include 2. But even though we don't include that point, we're going to leave an open circle. And I'm going to use that open circle and the point that we graphed out previously and connect the dots to generate the graph on the left-hand side. By having this open circle, we get to see where the graph is going as x gets close to 2. It's never quite going to get there because we have an open circle, but it's going to get infinitesimally close as your x's approach 2. Okay, so that's the left-hand side. For the right-hand side, we're going to do something similar. For the right-hand side, I'll be working with a green graph. One of the points that you can select is an x value greater than 2. Let's use 4. When your x is equal to 4, your y value is going to be 3 times 4 plus 1. That's 13. So when your x is 4, you're going to have a 13. Now I'm sort of going beyond the sort of scope of this graph. So let's say that 13 is right there so that it doesn't fly off. And you can choose any other point bigger than 2 to generate another point and connect the dots and graph the line. But again, I'm going to suggest that you plug in 2 into that function. So you'll have 3 times 2 plus 1, that's 6 plus 1, that's a 7. So when your x gets close to, or when your x is equal to 2, you have 7. So 1, 2, 3, 4, 5, 6, 7. So 7 would be somewhere around here. And in this case, you are going to include that point because the green function does allow you to plug in 2 in for those x's. If we had a inequality, if we had x, it has to be greater than 2, then we would have an open circle for that point. But since we have an equal sign down here, we will include that point, and with these 2 points, connect the dots, and that is the graph of this piecewise function. Often when you're working with piecewise functions, it might come in handy to use Desmos to verify your work. So let's see how to graph piecewise functions on Desmos. What I'm going to do is graph out the 2 elements individually. Graph out the negative 2x plus 3, and then graph out the 3x plus 1. So again, one of our graphs was negative 2x plus 3. And I want to tell Desmos to limit the domain so that you don't include every single point on that line. So what you can do is call up these squiggly brackets. And within these squiggly brackets, you're going to tell Desmos what the conditions are for those values of x. So for this part of the graph, your negative 2x plus 3, you want x to be less than 2. And notice that we have our graph, but it stops at 2. For our second piece, our 3x plus 1, that's our second line. And I'm going to tell Desmos to only use x values that are greater than or equal to 2. Now, technically, you could do this. use a strict inequality, x greater than 2, because it's convenient for me because the greater than button is on my keyboard. But if you wanted a greater than or equal to symbol to replace this guy right here, you can go down to the keyboard downstairs and pick it up from this template. Okay, so that's what the graph should look like. It should look like the red graph on the left and the blue graph on the right. I kind of like mine better.